Well, welcome. We're kind of moving into the more chemistry and society part of this class. And as I move on, we'll talk about polymers. So here are the learning objectives for this section. So polymers, macromolecules, that means big. So if you've heard of microeconomics and macroeconomics, macro means big. And polymer. So a polymer means many mers. Poly means many, and mer means molecule, many molecules. So a polymer is many molecules joined together for a larger molecule. There are a lot of natural polymers. So starch and cotton, they are polymers of glucose. Wood, it's got other stuff in it too. Cotton is almost all cellulose. Wood's got various other things. It's not entirely accurate, but all these things. So starch, and cotton, and wood, they are polymers of glucose, and they are joined differently though. So starches, of course, we can eat and we get energy from. Cotton, we can't eat. We can eat that, but we won't be able to get energy from it. We don't. Our GI tract isn't built for that. Other animals' GI tract can. Has to do with symbiotic relationships with different microorganisms in their GI tract can handle that. And proteins. Proteins are polyamides, just like nylons. Okay, so the first polymer, first synthetic polymer is celluloid, and it was originally with cellulose nitrate making billiard balls. It was originally called Bakelite, so we still use it today. And uh, but the polymer we use the most is polyethylene. So polyethylene, many ethylenes, and it is just a straight alkane. So I didn't mention this in organic chemistry, but alkanes are sometimes referred to as paraffins. And paraffins tend to be very unchemically reactive. So polyethylene in general is very unchemically reactive, and we use that much for food storage. Two types, high density and low density. High density is linear molecules very closely packed together, and low density is a branch used for various things, plastic bags. So lots of the plastic bags you see are mostly low density. High density polyethylene can used, I mean, like even television sets, not listed here, television sets and computers and whatnot made. So polyethylene we use quite a bit. It's used everywhere. And difference between low density and high density. So these two bottles here, one was high density, one was low density. Which one is which? The high density is sitting strong, and the low density is the one that shriveled up. Okay, so other types of polymers. Thermoplastic soften upon heating. Polyethylene is one of these. Thermosetting, they harden. So they harden when they're formed. So they do not soften. And I guess the definition plastic, the definition of the word plastic means it's moldable when it's molten. That's all plastic means. Metal is plastic, you could argue that way, but it's not a polymer. Okay, addition polymers, we'll talk about the different types of polymers. Addition polymers, we just add one molecule together on and keep on going. Polypropylene here is an example of one. And polyethylene is an addition polymer. It's the most common. Here is polystyrene, which is used in styrofoam. And here is styrofoam insulation, so it can be used for insulation. PVC, polyvinyl chloride. So this is what they use for the white pipes, the plumbing pipes. So PVC, polyvinyl chloride, is an addition polymer, and various usages there. Use PVC quite a bit. Polytetrafluoroethylene, also known as Teflon. So it's just like polyethylene, except it's got fluorines instead of hydrogens in it. And this stuff, it's hard to make. It makes on itself, and it actually auto polymerizes. The problem is that it's hard to control. it took us a while to figure out how to control this. We had a lot of explosions, but Teflon is I told you polyethylene is relatively unreactive. Teflon is even less reactive. It's also uh, fairly has a very little friction in it, so we use it for nonstick pans, and they use it for things where you really need a bunch of chemical inertness. So we use it in the lab. We coat things Teflon to make them very unreactive. Things like the stirring rods, the magnetic stirring rods are coated in Teflon. And if you've touched Teflon, you know it's slippery. So they use it for like if you want to have really heavy things to glide against one another. Teflon can be used. I mean, if it's even so strong that like metal is even too small, so they entombed Chernobyl reactors with a grate over it, and it was so heavy they used pieces of Teflon to slide the big cage, for instance. So here are the summary of some very common addition polymers. Polyethylene, the biggest one, made from many ethylenes, and we use this for almost everything. Polypropylene, carpets, these kind of luggage. We can also use polyacrylonitrile for carpets as well, so it doesn't have to be necessarily polypropylene. I have some polypropylene luggage. Polystyrene, so styrofoam. I think of styrofoam with this. You can use it for various things, though. It can be made for plastic utensils, for instance. You can also use polyethylene for plastic utensils as well. You can use a polyester called peat for that as well. There's various options. PVC, and this is used for various things. Yeah, garden hoses, floor tile. I always think of plumbing with PVC. Polyvinylene chloride, also known as saran. We use this for saran wrap. Teflon, already mentioned that, and polyacrylonitrile. So these for various synthetic fibers. Uh, Polyvinyl chloride, so various things, chewing gum, resins, adhesives, and polymethyl methacrylate. So not include. You can use it for those fake nails that people put on the nails, the fingernails. I mean, so this is plexiglass. This stuff smells when you're making it. Well, a lot of things smell when you make it, I suppose. And you can have conducting polymers. Polyacetylene has a conjugated single double bond. Conjugated means alternating, so you can see there's an alternating single and double bond. This means then that it can conduct electricity. The electron cloud becomes very diffuse here, and then that electrons can then flow in that very large electronic cloud. So plastic means you can flow under heat and pressure. And as I mentioned, you could argue that metals are in fact plastic. But when we say plastic, we usually mean uh, uh, polymers, specifically synthetic polymers. So compression molding, you can just take a powder and pressurize it, and it'll form whatever it is you want. Injection, you melt it and inject it into something, and in a cold mold. So a lot of like television sets are made this way. The at least the plastic coating for television sets. Extrusion, so you put it through like a it's I think of I remember there was this Play-Doh thing when I was a kid, and you push on it, it made something like spaghetti. You have a hole and you push it through, you make spaghetti. This is by definition how you make a tube. So if you ever want to know the difference between a pipe and a tube is extruded and a pipe is welded. So we use this kind of sometimes interchangeably. Like we call it the tube in the center of like the toilet paper, but toilet paper center is actually a pipe. If you look at it, at least the ones that I use, it has the sheets of paper that are like kind of glued together. So that actually makes it a pipe. Tubes are extruded. So a lot of uh, tubes made for various things, car engines, gas things, have liquids. Those are made by extrusion. Pipes you weld. Pipes tend to be bigger, so for pipelines, that kind of thing. Take a flat sheet and then curl it around and weld it along the seam. Blow molding, you make a bubble. This is often how bottles are made. So you can also do this to make glass. I took a scientific glass blowing class. It was kind of fun. Of course, using glass for blow molding instead of plastic. Uh, so elastomers, these are polymers that if it is subjected to tensile force. So the idea is that you have like a bunch of jumbled up uh, molecular chains, and when you pull on them, they all turn straight. And then when you let go, then it returns to its original shape. So a lot of elastomers. So nitrile gloves, latex gloves. Latex is a rubber, so rubber is what we usually think of with this. So and rubber is an elastomer. Natural rubber is polyisoprene, but we can make it stronger, and this was done accidentally, adding sulfur to it. So Charles Goodyear found this out, and it was one of those mistaken discoveries. And this shows the elastomer. You see the chemical chains here with the sulfurs in between them. If you pull on these will all turn straight, and there's the elastomer. When you let go, it returns to its original shape. Uh, and sulfur, if you put on things, it smells. When sulfur burns, it smells really badly. So Charles was probably very upset the first time he spilled sulfur into his rubber tank, or his big vat of rubber, and then like, hey, wait, this stuff is actually better. He called it vulcanization after Vulcan, the god of the forge. So the weapons maker of the gods, the Hephaestus in Greek, the volcano god. So synthetic rubber, it's depends on what you're doing. We have nitrile gloves, for instance, and can have polybutadiene, various synthetic rubbers. You can also have silicones, which we can talk about later. Neoprene, and it's much more resistant to gasoline. So neoprene is similar to that, but it's stronger for specific applications. It's also I have seat covers that are made of neoprene in my car. So styrene, butastyrene rubber, it's tougher than that, and it's much more resistant to oxidation. And it's not as satisfactory in terms of its mechanical properties. So chemically it can be great, but mechanical, it's not the best. So elastomers can be used in binders and paint. So the way that painting works is and it's actually also was referred to as a non-Newtonian fluid. At least latex paints are. So if you apply pressure to the latex paints, the viscosity decreases. The viscosity is resistance to flow. So you apply pressure, and then the paint goes on the wall, and it flows more easily with the pressure applied. Then you take the pressure off, and the viscosity increases. It sticks, and then you have the monomers inside the paint, and you have the solvent for many paint. At least the paints I use in my house, we used water-based paint. I mean, if you go to any paint store, they're going to be water-based paints. But then, but you can also use paints that have hydrocarbons as the solvent, and then the solvent evaporates. The polymers polymerize, and then it holds the dyes in place. So that is how your painting works when you have your paint and dry in your house. And condensation polymers, these, when they react, a molecule pops off. And condensation polymer specifically is water. So, I should say almost always water. But condensation polymer is a small molecule, and it's most frequently is water. And nylon is that, and polyamide. So the same thing with proteins. So protein synthesis is an addition polymer in your body, and water pops off whenever protein is made that way. The opposite is also true. When you digest proteins to form amino acids, your body has to add water to it. It does it with either a catalyzed reaction with an enzyme, or the even better in your stomach. If you add the acid, can help break down the protein bonds. And then a polyester, so many ester, has an ester linkage, where you have the carboxylic acid group connected to a hydrocarbon. So here is polyethylene terpentholate. This is known as peat. This is known. This is what a lot of soda bottles are made of. Are made of peat. So if you look at that, and a lot of kind of high quality uh, sort of plastic cups and like uh, cutlery are made from peat as well. They can be. They can make them from polystyrene too. It just depends. I mean, you have to look at the plastic and to see which kind. It'll tell you in the recycle symbol which one by the number which one it is. Phenol formaldehyde resin. This is Bakelite. Oh, I said that was the. I'm sorry. I referred to that as the the nitrocellulose. Um, but I made a mistake there. I apologize for that. Uh, Bakelite here was the first one, and I used it because I used it for billiard balls back then too. It's kind of replace ivory. Okay. And formaldehyde can make urea formaldehyde resins and melamine formaldehyde resins. So these are other types of resins. So resins, I kind of think of sticky things when I think of the resin, uh, whatever if you want to know what it is. Polycarbonates. These are used to make tough things. So helmets, safety glasses, dental crowns. I mean, you can also use a lot of dental crowns are made of gold and also various other things as well. But uh, you can make glasses from these, not even safety glasses, but like plain old glasses are not usually made of glass, but polycarbonate. At least the relatively inexpensive ones are. So polyurethane, similar to nylon, so make for foam rubber, skate wheels, and tough furniture finishes. Like you can use paints. Whenever I make my own furniture, sometimes I buy a uh, cheap furniture somewhere, and then I can coat it with polyurethane. So to make it tough and more resistant to water, especially if you put the furniture outside. Epoxy resins, so two-part liquids, and then they react together. And these are great for adhesives. We use epoxy resins also for dental fillings. Uh, like we used to use mercury amalgams for dental fillings, and nowadays we've been going more towards epoxy resins for dental fillings. And usually you need photons to start the chemical reaction. So you need to mix them together, and you also need ultraviolet light. So you put it together and you stick it outside, or if you or you use the light in the dental office when they give you a filling. Uh, I I've used epoxies. Like I had the rear view mirror come down from one of my cars, and I couldn't get the stick. I used the kits a few times. I just got some epoxy resin, and I put that on the rear view mirror, and that thing didn't move. That's the last time it fell down from there. So epoxies can be very strong. So composites, these use fibers that are in a polymer matrix. So Corvettes, for instance, they have fiberglass and composite together. So uh, that's why if a Corvette, don't hit a Corvette. I've never hit a Corvette, but they can shatter because of the panels there. So things, yeah, like tennis rackets and such on fishing rods. If you've seen them, they have like these fibers in them, and that's the composite material. And silicones, it has silicon rather than oxygen, and it kind of it's a silicon oxygen chain though, because silicon, it's not like it's a polyethylene. Like if you look at polyethylene, if you put silicon rather than polyethylene, if you do that, it'll just be a big ball of gunk. It'll just turn into silicon if you do that. Actually, you have to have silicon oxygen bonding, so the silicon is not really bonding to itself like carbon does, because carbon's unique in that where it doesn't really, well, it won't form where it forms a straight chain. Silicon won't, so you have to have oxygens between them. And the smaller ones tend to be the synthetic oils. The bigger ones and also the cross-linking ones tend to be the uh, solid ones. So it depends. The longer chain and the cross-linking ones tend to be like the silicone solids, and then the shorter ones and also that are not cross-linked tend to be the oil stuff and conditioners and that kind of thing. So polymers, they have very, very high molecular weights. They're big molecules, so the number of molecules per mole is very high. So with that, they have relatively strong intermolecular forces. So, and they can, at least, I mean, for the big ones, I mean, I know that, well, obviously synthetic motor oil does not have very viscous solution. But that's because it's a smaller molecule. But the big molecules, they are pretty good at sticking in place. And crystalline polymers like high density polyethylene, a little bit more crystalline than low density, those tend to be very, very rigid. And an example of a crystalline polymer that's natural is a diamond. A diamond is a crystalline polymer of sorts. Amorphous polymers, and they tend to be more rubbery. So the marked B there in the bottom, that's kind of like the elastomer. If you pull on that, it'll actually look more like the A portion of it, and then you let go, it'll return to its original shape. So the glass transition temperature, this is where the polymer becomes tough and rubbery, and below it's like glass, hard, brittle, and soft. So some polymers you can continually heat them up and mold them again. Some you can't, but it just depends. The glassy temperature. So glass is kind of like a solid, kind of like a liquid. It's an in between state. We give it a glass. We call it's glassy, glass property like stuff, and the well glass. Glass is still kind of an in-between kind of thing than a solid and a liquid, although we tend to think of it more of a solid. But glass can flow, and uh, but very, very slowly. Glass is like a liquid with extremely high viscosity. And many of these synthetic polymers can be used to make fibers. So much of the fibers used are synthetic, and I mean, you think about your clothing. In fact, I'm wearing cotton clothes right now, but I mean, think of what else we have made of fibers: carpets, rugs, and these types of things. So this is synthetic, and nylon. We have lots of polyesters, lots of nylons, lots of fabrics that way that are not necessarily cotton. And one thing about the plastics are great. We designed them such that they're very resistant to chemical attack. And the problem with that is when we get rid of them, they do not decompose very quickly. So you throw a banana peel in the trash, it starts to break down. Plastic, though, can take a very long time to get rid of. So how do we get rid of them? We can incinerate them. Plastics tend to be burnable, but the problem with that is also many of them, like Saran and PVC, have chlorine in them, and that forms hydrochloric acid. So that's some pollution when you burn it. So plastic disposal is a big problem, and an issue with this is what do we do? Uh, I mean, we are starting to move away from single-use plastics, but we use so many single-use plastics. Just for food security. You you put like when I buy strawberries at the grocery store, it comes in a plastic container. I don't use that for anything else. And what are you going to do with that plastic container? Do you send it back and like how much like the energy that it costs to ship it, and you got to clean it, and clean it usually use water. Is the water waste used by cleaning the plastic and then shipping it? Is that energy loss in that, is that recoverable? Is that by not making more of the plastic? And the other thing with the plastic is it's a byproduct from the polyethylene, at least, is a byproduct from petroleum manufacture. So if we get rid of plastics, polyethylene, what are we going to do with the ethylene? I mean, we just go back to burning it. So that's another thing. What do we do with this? These are some of the hard questions that we have with environmentalism and sustainability. So we can burn things, but I mentioned that like saran and PVC will generate uh, the hydrochloric acid when burned. And it does depend. Some of the stuff doesn't burn very well. Rubber tires do burn. Of course, they burn with sulfur, but you have to scrub the 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 gas coming out. That's the point of that. Some of them, so some plastics are degradable, and lots of our waste come from packaging. So maybe we'll use biodegradable stuff in the future. And the problem with biodegradable plastic is if it's put deep in the landfill, it still degrades slowly. So this is not necessarily a good solution. The good solution is more reusableness of it. And recycling, I mean, so this is the best option. And to uh, get rid of single-use plastics. That's a push that we're doing right now, and the consumers seem to be following. They like this idea, and a lot of recycled plastic, though. I mean, a lot of it is recycled just right in the factory, so it makes sense because when you're making things like the raw material for plastic frequently are like little pellets, and then you throw the pellets to melt them into an injection molder, and there's a little bit left over. Like you have these odd pieces, and you cut the pieces off of where the television was put in the injection molder, and these types of things. And what do you do with that plastic you cut off? And what many people do is they just throw it right in the hopper and melt it back down. So that's an easy way to recycle things. Some places depends on the um, on the specifications of the purchaser of the plastic, the molded plastic. Some of them say we do not want any recycled plastic in here, but people are now, of course, going more and more. And if you see it says made from partially recycled products, that's usually what it means. It's just recycled right there in the factory. And that's I mean, of course, that's the best. It's a really good idea. It doesn't decrease the value of the product at all, or any of the functionality of the product. Uh, when you have recycled products, so many times the products are of lower quality, especially if it's been used. But there are some plastic things that we have that we really don't care about the quality of it. An example of that is like garbage bags and garbage cans. I mean, I don't know how many people say like, you know what, I really want to have a fancy garbage can. You know, that's one of my goals in life is that I can get enough money and I can buy a really cool garbage can. Right now, no one. I mean, depend. Maybe some people do care about that, but I sure don't. You know, like that's an example of a low value product. So we can take uh, plastics and turn it into a lower value product. And of course, plastics are flammable, and this is a problem. And many of them release toxic gases. So that's one thing. And you probably know this that a majority of injuries from fires come from the inhalation of the gases. So when they tell you, one of the things they say, if it's smoky in the room, sink to the bottom of the room. And doing so, you don't breathe in those gases. So you do not want to breathe in the gases from plastic. Not mentioned in this slide, we mentioned hydrochloric acid, but it can also form phosgene. Phosgene was used as a chemical weapon in World War I. So if you start burning polyvinyl chloride at a high enough temperature, it can turn into phosgene, and that causes some other effects. Like I said, it's a chemical weapon. or it was chemical weapon. And many polymers are soft and brittle, and then you can use plasticizers to make them much more flexible. So a lot of clothing. So people say, "Oh, I've got plastic clothing." They use plasticizers on there, and these, as they vaporize, the materials become stiff and brittle. So you notice that when things get older, they don't get as bendy anymore, and then they start breaking off. That's because those plasticizers are going away. And we used to use PCBs for plasticizers, but now we are moving more to phthalate esters. So these are the more common ones that we've been doing now for the plasticizers. And the toxicity, even though the PCBs, these are still low toxicity. So, but these seem to be lower. And much of this, though, is unknown. We do not know the extent of the toxicity of these molecules. And it's really hard. I mean, we are trying to get rid of single-use plastics, but I mean, we use them so much. And I mean, they're wonderful. I mean, when I buy drugs, if I want to buy a bottle of aspirin, a bottle of ibuprofen at the drugstore, I it's made of plastic, and I mean, it's a single-use material. I mean, I don't think we're going to start a recycling program for that. I mean, maybe I guess they use plastic bottles in the pharmacy, and maybe those could be recycled, but still, there are some risks associated with that. And I mean, I rip the plastic seal on the plastic bottle to make sure it's safe, right? And then it has a little cotton ball in there, and I pull it out, and then I have really fresh drugs that I know have not been tampered with in there. So, and I buy my strawberries at the store, and they're made of plastic. Plastic are light; they don't react. So, what if we used glass? Glass is very reusable, but there's some issues with glass. It's heavy, right? So that means it's going to burn more fuel to ship it. And if I drop a plastic container, the plastic doesn't shatter. If I'm barefoot in my kitchen, I drop a glass container, it can shatter, and now I can step on the glass. So I mean, there are some things that are more dangerous about it. So this is a tough problem. Is how do we how do we change our habits? How do we? I mean, our world is so ingrained by these single-use plastics, and they work so well. I mean, look how thin a little sandwich bag is. They're super thin. They're made of plastic. They're light, and I can buy 100 of them for like a few dollars, right? So I mean, though Tupperware is plastic, I reuse those. So, but I mean, I must admit, I do. After a couple of years, I throw them away. So then it goes to the landfill. So uh, these are some problems. These are some problems that we think about, and we're trying to figure out whether the most environmentally conscious way to do things, the most sustainable way to do things. And we're working on it. And that is one of the aims of green chemistry here. So, and we are done for the current one. Join us next time for nuclear chemistry.